Hello, everyone, and welcome to the Lightning Talks. Today, we will be covering intelligent edge use case. Let me introduce myself. I'm Sumitra Bojan. I'll be the moderator for this session, and I'm also a co-lead in the telco group in OCP, and I also work at AT&T. Let me introduce the speakers today. So first off will be Brian Zunstecker. He's a principal engineer with PowerRox. Then we have Benjamin Wang, special assistant to CEVP and 5G IDM BU head with Foxconn. Yusuf Avar is an edge segment lead with Intel. And we have Dirk Blevins, senior platform architect, principal engineer at Intel. So like I said, today we have a set of speakers who will be focused on giving a presentation on the intelligent edge cases. So I'm going to hand it over to Brian. Here you go, Brian.
All right.
Take it up.
All right, Sumitra, thank you very much. Thank you for the introduction, and to the OCP for having this, and for the makeup session here. Sorry we didn't get to do this face to face. Just a quick intro of myself. As Sumitra said, I'm Brian Zunstecker. My company is PowerRox, a power electronics consulting firm based in San Jose, California, in Silicon Valley. And I have a various background all around power electronics, and power and energy efficiency is my main bag. So I came from the data center world doing server power for folks like HP and Cisco and Emerson, before establishing my own consulting firm and focusing on ultra low power energy harvesting IoT type of electronics, as well as 5G network power and all that, which I will pull all that together to lead into the discussion today. Next slide, please. So, so most of this talks about a concept we refer to as the 5G energy gap. And we'll formally kind of define this in a minute. But to understand kind of the motivations here, I think it's important to really understand the true cost of, like I said, even a mere milliwatt at the edge. So go ahead and click through a few times, Sumitra. And you can click a couple more. So in summary, one more. So in summary here, what this is saying is that you imagine what having a milliwatt of received instantaneous power at your edge device, say your smartphone or whatever. So if we follow that all the way back up through what I refer to as the power value chain, which we'll be showing you graphically in a second here. Said if you back that up between what it takes to have that transmitted power from the base station, and then the second bullet there showing the how that would translate to the input power of the base station. And by the way, these ranges are best to worst case, using very conservative kind of napkin math. And then the third bullet refers to just the loss in transmission. So the takeaway from all this is that for each milliwatt of received power, what has to be generated by the power plant is on the order of 18 to 60 watts. So now we're talking, that's 4 to 5 orders of magnitude of that has to be generated just to have that instantaneous received milliwatt at the edge. And so that multiplication factor is something we refer to as power cost factor, or PCF, as it's showing there on the right. So remember, this doesn't even take into account the actual the energy to compute. That this is data that needs to be crunched and transmitted, and the overhead that's associated with that, and the data center and anything else. So at the end of the day, you're really talking 5 to 6 orders of magnitude that you kind of pay, and that's this power cost factor. And when you talk about deploying, many billions or even 1 trillion devices, especially with so many in a densified single environment, this really starts to add up and matter. Next slide, please. So as a further motivation for kind of the point of this, this is the reason in this power value chain, as shown graphically at the bottom there, of why following this power value chain, if you see the graphic on the bottom, on the right-hand side, as it said, towards the edge where user equipment is. This was this power value chain we were following back, going left all the way to the power plant on the left side. So at the bottom, you can see that increasing power cost factor increased from the edge. And in fact, right at the very first box on the right, where it says user equipment, between the user equipment and the radio, I mean, depending on how you look at it, this could actually be anywhere from 0 to 6 orders of magnitude alone, just in this stage, depending on the use case. But so much is lost, particularly in the radios and the base station, mostly due to the linear power amplifiers, which is why, as this first bullet states, realize that globally, all the global energy of all ICT telco equipment, that means that includes, everything from phones and edge stuff to the core networks and data centers and front haul, back haul, all that stuff. Base stations consume 60 to 80% of that for this very reason, that they're horribly inefficient and they're everywhere. Click, please. So this is why, small cells, especially as we talk about the migration of 5G and to heterogeneous networks or HETNets of smaller cells all kind of working together and playing nice in the sandbox is a real opportunity. And luckily, it's also the one that has the biggest opportunity for dynamic power savings. Next slide, please. So this disproportion in kind of the between the demand and the load is what I'm referring to as the 5G energy gap. So we defined the power value chain. We mostly talked through it, so we won't spend much further time on this. But we saw as showing kind of energy flow end to end through all the black boxes and conversions and all that. So we understand kind of what that looks like in a big picture. And the 5G energy gap is really more of this, think of it being on the load side towards the utility grid side of things, is this concern that all these, many billions of tiny devices and tiny power devices on the edge are going to disproportionately demand such a high amount of energy that, potentially the utility grid won't even be able to source it. And worst case scenario is that, you actually have grid stability issues as a result of deploying all these many, many tiny power devices. So that's what that 5G energy gap is about. Go to the next slide, please. Now, there's kind of a more economic way of spinning this, which is to say, well, okay, yeah, if I could give base stations the unlimited amount of energy they'd request, that I may have that utility problem, that 5G energy gap. But let's look at it from the load side for a second and say, well, the devices, the systems, the base stations themselves are essentially power limited and thermally limited for their actual design. So it's to say it doesn't matter how much the UEs and the load will ask, there's still a limitation to the base station itself, which means that that's a power limitation, which is going to limit the amount of power coming into the base station. And therefore, it's going to limit the application of stuff on the edge, and the hooks and all the processing and all the other fancy things we want to do. We'll have to scale that back if we are power limited, and that has a great deal of impact on the kind of the economics of the payback period. So that's why we refer to this as the 5G economic gap. And then that also translates to, socioeconomic disparity, because we don't want to lose sight of that too, that this energy limited problem could also be an economically limited problem. And if people in certain regions don't have the resources to handle and account for this, then it will lead to major socioeconomic gaps. And that's what we're calling the 5G equality gap here. So for sake of time, though, we're going to move through this. And by the way, at the end, there are some resources we'll refer to that will kind of allow you to get into this stuff in far more detail. So next slide, please. So we wanted to I want to take some of those concepts and translate them into proposed metrics that can enable people to start assessing this stuff from both technical and economic perspectives. So one, as I mentioned earlier, is this idea of power cost factor, to say if we just take any point in that power value chain, any one of those black boxes, and try and assign kind of this power cost factor as it relates to its energy generation, then we get right in that black box of wherever it is in that value chain, we get an idea of kind of how, what its overhead cost based on where it is in its application. So you could apply that whether you're designing a system or you're doing the economic payback period analysis of deploying base stations, or even network level analysis and deciding if you want to optimize for real-time energy markets. It's kind of a unitless factor that transcends all these barriers, as well as those other factors. And so that leads to something we're referring to as a 5G D-rate factor, which essentially says that there's the maximum design capabilities of your network, but then due to these energy and economic and socioeconomic limitations described, there may need to be a D-ration to more effectively model the success and economic payback of any 5G deployment. So next slide, please. So with that, I'd like to introduce something for consideration by OCP, especially the Telco and Edge group, which is to say that there's a justification for essentially a dedicated OCP, basically a 5G small cell. So we need someone with a lower power budget, because as we go from the macro cell model to these small cells, we are essentially, migrating all this stuff to small cells. So we're going from higher power stuff to lower power stuff. And the lower the power envelope of the system, it's actually a better opportunity for intelligent power management, turn things on and off, and to be more reactive to real-time traffic patterns and all that, to optimize energy savings. And we don't have time to go into what those techniques, many of those techniques would be, but this is just making the point here that these small cells are essentially going to become full data centers, as well as software-defined and NFV, network function virtualized devices and software-defined radio devices that will have to, not only intelligently manage the spectrum but the data as well. So to enable things like edge buffering and mobile edge computing, I make a mention of energy harvesting here to help supplement power budgets at the edge to mitigate the 5G energy gap concern. Something like this is what I would propose to help standardize that, because there's going to need to be so many millions of these things out there eventually. So click. And as it says, this doesn't exist, but this is something hypothetical for the group to think about and to address this call to action. So speaking of calls to action, I'd like to close my talk to encourage you to really think about how you might be impacted by this 5G energy gap. As we said, it really reaches every aspect of the ecosystem, whether you're an equipment operator, you're an MNO, a network operator deploying stuff, or you're a data center operator, or you're a utility grid. And you got to really ask yourself, how am I energy limited, power limited, socioeconomically limited, all the above? Click. So it really, the whole point again is to put a new spin on the economic and business models too, and to consider that some of these proposed metrics like the power cost factor and the 5G D-rate factor. And energy and power crosses all verticals and everything, so it needs to be considered in all OCP groups in the full ecosystem. There's a link there for the telco mailing list, so you send an email to this shown here, and to find out more information and to find out more specifics about the 5G energy gap itself that I've described as a link to a short article. And please feel free to reach out to me. My email and contact information is on the first slide, as well as I'm sure will be included with the materials that you receive for this. And hopefully, this part was pre-recorded, but we're gonna have a live Q&A session and all that. So hopefully we're about to have a lively discussion after I turn it over to my next, our next speaker here, Dirk. So Dirk, I'm gonna turn it over to you.
Thank you very much, Brian. Appreciate it, and very informative presentation, and definitely making me thinking about the 5G energy gap, as this is something that I deal with, and I think you'll see some of the things we're going to talk about in a minute actually play into some of those decision factors, you know, so thanks again for that. With that said, Ben and Yusuf today prepared this presentation. They weren't able to make it, so they asked me to present it for them. So we're going to go ahead and move forward with that. My name is Dirk Blevins. I'm a senior platform architect and principal engineer at Intel Corporation. I've been at Intel for 20 years, participated in many things over the years, but my expertise at this point in time is focused on edge solutions, up to including you know, mobile edge computing, as mentioned before, down through you know, UCP, SD-WAN, and things of that nature. So hopefully we'll find this in the next section, which I'm also going to present, very informative. Please, next slide. So with that said, what is the Converged Edge AI and 5G wireless access for a smart factory of the future? The overarching concept of what we're here to talk about in this particular use case is, you know, the needs that are starting to evolve given the capabilities that are starting to exist within communications infrastructure. It also looks at how that communications infrastructure can move into operational excellence and operational technologies through using applications related to artificial intelligence, as well as introducing the key capabilities, the transmission medium, such as 5G wireless capability. So when you look at this, you're looking at solutions that are starting to present themselves, and these smart factories are becoming smarter and smarter and needing to process more and do things more efficiently and more quickly. Well, things such as 4G and 5G wireless technology, be it private or public, give you the capability of lower latency, better bandwidth, better jitter control, things that are all important to manufacturing. And then you couple that with the ability to have analytics, you know, such as some video data that can be taking telemetry and basically making intelligent and real-time decisions based upon that. You then put in the private wireless aspect so that you have your own private network for security. You have a pretty powerful situation that allows you to do that. Now, going back to where, you know, what this is taking and where this goes, and kind of, you know, what Brian was referring to a moment ago in his presentation is that, you know, this is all going to have to be done, you know, through, you know, intelligent infrastructure, through SDN, through NFV, because these things are evolving and changing, and the types of applications that are required they're going to be required to be able to be adaptable. And that's where we hope that Intel is providing the solutions that allow this adaptation to take place. So what we're going to talk about a little bit today is a demonstration and showcase that we were going to show, but it's more of a real application that Foxconn Technology has developed using Intel capability and 5G wireless infrastructure and AI, as well as all the Intel foundational components and open source software in order to deliver the smart factory of the future. Next one. So what's required in this solution in order to make something like this happen? If you look at the graphic that's on the left, you know, in this kind of a solution, you're still going to have access to the public cloud. You're going to have access to a private cloud, because, you know, in an industrial environment, in a factory environment, you know, these things can cause real damage if something goes wrong. I mean, it's, you know, I like to equate it to, I'm going to show my age. We used to have blue screens, or we used to have routers we have to reset. That's not what happens in a manufacturing environment. You know, if something goes wrong, somebody gets hurt. So we have to have tight control. They have to be secure networks. You have to have this capability. Well, it all starts at being able to understand what the communication technologies you are that are driving over the particular solution. With that said, there's still going to be Wi-Fi infrastructure. There's still going to be things that's required on these factory floors. There's going to be monitoring cameras for security aspects, various other things that's currently done. But to a lot of the key things that you look at, you know, whether it's, you know, trying to control an AGV, you know, automated guided vehicle through a manufacturing floor, or, you know, trying to understand, you know, different sensors or how things are happening on the manufacturing line, it takes tighter control. It takes higher bandwidth. It takes lower latency. It takes jitter control. It takes all these things. And then you have to be able to converge that and be able to bring that together in a fashion. Now, in doing that, you know, you're going to have this a piece of a deployed public cloud infrastructure as well as a private cloud infrastructure. It starts at the Converged Access Edge server, which is what we're here to talk about. And we'll talk a little bit more about the software intelligence here. But then you also have your 5G NR distributed units as well. That's servers also that's being deployed on Intel technology because they need flexibility and the ability to be able to retrofit into different dynamics. But you need both aspects in order to be able to carry that out. And then in addition to that, you then start to need to understand how the intelligence is, because, you know, just because I have this capability, certain things like this can exist today. But if you don't have the intelligence and the artificial intelligence and the ability to do something with it, you know, it doesn't really matter that you have these particular fixed function aspects. So that's where, you know, you look at understanding like imaging technology and where that can come into play, and understanding what's going on and monitoring, you know, what's happening and taking telemetry and statistics and how that can be used to create truly autonomous self-learning applications that, you know, kick off monitors for errors to shut down the factory, or to kick off corrective measures in order to be able to bring, you know, certain elements back on the factory. And that's where the software stacks. And if you look at the ingredient stack, it's on the right-hand side. You know, this all starts based on Intel technologies at the processor, at the SSD level, at the Ethernet control level. We've taken great care in the definition of our products to look at this truly from a system level implementation and try to work backwards into understanding the overall solution. And when we look at this, you know, if you take the distributed units, you look at what's being done there. These are normally just standard Xeon SPs, you know, with maybe FPGA technology or, you know, certain Ethernet NICs that are introduced into the solution that then run a FlexRAN software stack. Well, by having FlexRAN, you know, depending upon whatever your deployment wants to be, you could be deploying LTE, you could be deploying, you know, your 5G services. So this is how some of that adaptation and not having to deploy multiple different pieces of hardware and understanding how to orchestrate those things and deploy them differently, you know, because you're running on a common subsystem that allows this to happen becomes important. And then on the right-hand side, when you look at the Converged Access Edge server, this starts by having, you know, software solutions that Intel is working on through our openness, you know, type platforms, to where, you know, we're starting to put in mech controllers and, you know, things of that nature to allow you to configure these subsystems easily, and, you know, without too much trouble. You know, on top of that's built, you know, Intel technologies and accelerators that, you know, directly and seamlessly tie into these different software, and a lot of these open source solutions, stepping up through open source OBS solutions, open source operating systems, you know, Ubuntu, CentOS, and those types of things. And then on top of that, you end up with microservices, and these microservices then allow capabilities such as OpenVINO, which is an analytics suite, open source analytics suite that Intel contributes to a lot. You know, you may do facial recognition for security, as an example, for people to get on certain elements of the manufacturing floor. You can also adapt this technology to be able to look at telemetry of what's going on in network infrastructure, of what's going on the actual manufacturing floor, to look at that imagery and make intelligent decisions. And then finally, you look at the open source software that ends up doing determination of the different things, the virtual EPC, you know, the FlexRAN software, things of that nature, in order to be able to pull this whole picture together. So these things need to be highly configurable, highly flexible. And then the final piece is the Converged Access Edge controller, which allows you to have APIs to easily onboard the applications that you may want to develop on top of these particular solutions. Next, Will. So as we look at this, what's the summary of what we're trying to pull together? Well, it's the incarnation of, you know, looking at how to start to put together this infrastructure to allow these things to evolve over time. If you look at what's on the left, this is its infancy. This is the demonstration that we were, you know, kind of bringing forward, and what Foxconn absolutely can share with you with their solution built, you know, on open inspired hardware. With that said, as we look to the future, you know, this has got to evolve. This has got to become more sophisticated. It's got to start to understand what's going on, at every level. It could be from inventory management. It could be to, as I said, AGV control, with what's going on there, production line issues and issues of what's happening, but on a manufacturing floor, this stuff has to operate, and it has to be very, very low jitter, very low latency communication, secure, and be able to communicate with each other. So having that capability in 5G allows that capability, along with the capability to have advanced analytics in order to allow certain artificial intelligence type applications to be ran. It kind of brings together the whole picture. But when you look at this, you want to be able to spin these things up easily and quickly, and that's where a cloud native architecture that Intel really excels in comes into play, because we have the capabilities and the services through open infrastructures to be able to evolve this and bring these things online really, really quickly. And then finally, look at the operational efficiencies that could be gained, by introducing this kind of technology and capability. If you look at what's happening, in the industry, there's certain applications with the introduction of 5G that could have never been dreamed of before. Now that that's here, it's going to get into situations that, it's going to bring about the need for advanced analytics and advanced telemetry and artificial intelligence in order to be able to pull off these particular applications. So with that said, I'm going to bridge into the next piece of this, which is about the Open Edge working project that we have and some of the elements we're doing for some of the underlying hardware, actually, quite honestly, for some of the applications like we talked about in the smart factory. So if we proceed ahead. So I'm actually a professional musician, moonlighting as an engineer. That's not true, of course, but that's what I like to think, of course. But with that said, one of the applications I've dreamed of for years is a virtual band. I came from college and used to play in a band, and life was really, really good, and we loved to play music, and that's all we cared about, and trying to pass engineering classes. With that said, when we look at these different solutions, latency, bandwidth, jitter has absolutely prevented this of being at all a possibility. It's just not capable of occurring because of all the latency aspects, the jitter aspects, and the lack of bandwidth. You had trouble being able to pull different solutions together, being able to mix these solutions together, taking untethered streams, and even doing the time synchronization to bring these things back together. So if you can imagine somebody that's, on one side of the country playing the guitar, and they start off the song, by the time it gets to the drummer, he can hear that properly, that's fine. But then the bass player, whenever it's coming to the drummer, is out of sync with that, So that's where the aspect of also, it's not just enough to have the 5G network. You also have to have the ability to be able to stitch these things back together, pull these things back into a situation that allows you to reassemble, this type of thing. So when you look at that, that's going to step into two different elements. First off, it's going to require some pretty advanced analytics and pretty advanced artificial intelligence to be able to pull this together. You might say, well, they've had mixers for years. I'm not talking about that level of thing. What I'm talking about when I'm talking about the artificial intelligence is the network itself. When you look at the network itself, you may be having a good connection with certain bandwidth, but there may be parameters that come in that change that jitter or that latency or that bandwidth. And you have to be able to dynamically switch, to a better circuit, or dynamically switch to a better network environment to allow this to be able to continue, to allow you to be able to, run your operations. In addition, you do have to also have some intelligence to be able to reassimilate these packets, and put this information all back together, and be able to push it out to the edge. Now, this has to be a distributed intelligence. There's no way to do this from a centralized environment. It's just not possible, in any way, shape, or form. You cannot start by all three instruments I'm showing here playing up to a centralized location in a data center and then trying to replay those back out and then work efficiently. It's literally just not possible. So that comes into understanding what the hardware at these edges start to look like. because in order to realize this, this is going to have to take place, and that's where the open edge and the work that we've been doing there plays into that particular scenario. Next foil. So what have we been doing in the work in the Open Edge working group underneath the telco group within OCP? Well, one of the things we've been focusing on is trying to develop additional sleds. So whenever we look at what's originally proposed and what's there, it's shared compute, it's shared storage, it's shared power, it is shared cooling, it is shared management, but it did not share the compute and storage elements, other than they created this concept of these sleds that you could plug into the solution in order to personalize the device for what you needed it to be. You know, if we needed it to be a small cell, you may configure it with certain elements. If you needed it to be, you know, more storage focused element, you could configure it with potentially different elements. However, where we're at in the evolution of this particular specification is that it's mostly focused around compute and the sharing aspects. The concepts of storage sleds or accelerated cards, you know, for RAN acceleration, wasn't brought in for general purpose PCIe, somewhat brought in into the compute sled scenarios, but say you need more than what the compute sled offered, then you have to be able to do that and deal with network latencies, things of that nature. So the focus where we've been looking at is how do we start to develop these sleds and these new concepts in a different fashion in order to be able to bring them together to allow more innovation, more flexibility, and to be able to realize applications like I just described. You know, without the capability to have more intelligence and more processing, you may need, you know, if you want to do video aspects, you may need to have transcoders that's co-located alongside of these particular compute sleds, and you may want to do some, you know, buffered storage depending on what your application is, you know, for certain deployment methodologies. So, you know, when we look at this, that's really where we're focused at. And we're also trying to focus this in such a fashion to be able to gather the requirements. We're not trying to reinvent the wheel. We're not trying to, you know, do something that other specifications have defined. We're trying to come up with a way to better deploy these applications in a more seamless fashion, a more configurable fashion, more flexible fashion, and allowing sled-to-sled compute, allowing, again, those graphics cards and PCIe cards and FPGAs and storage devices to be more seamlessly integrated with these particular solutions. Next foil. So finally, I'm going to try to wrap up both sessions here. You know, what can we do and how can you help, you know, move these solutions forward? Well, you know, there's a lot left in the definition of these things. We're just starting. We've been working on it for maybe a couple months now, 2 to 3 months. You know, we're trying to figure out how we do this. We're talking to various people in the industry, service providers, industry bodies, et cetera, trying to understand what these requirements need to look like in order to make these solutions move forward. This gets down to levels of understanding, you know, the types of sleds that's required, and, you know, how you're required to manage it, or how you're required to load firmware and to, you know, understand telemetry that's going on with the solution. Understand the environmental requirements and the electrical requirements, power requirements at these endpoints in order to be able to design a better system, to design these things that will look much better and be much better, more flexible, more capable. Also defining the interconnect requirements from sled to sled, allowing you to be able to talk, you know, from one chassis to the next chassis, because you may have a multi-chassis deployment in some of these environments depending upon what you're doing. So these are the things we're looking at. And if you would like to participate, you know, a few things we have going on is obviously we have the Open Edge sub-project, which Mike Moore runs monthly. Would encourage you to join the Open Edge and start to participate in that working group. We have some really lively conversations in there. In addition, we had started, Intel and Nokia in particular had started working with AT&T to start to develop a particular document that went into more details on the definitions of these sleds, types, configurations, et cetera, and you can see Mike's been helping us there along with myself and Suha. In addition, you can send direct questions to the OCP mailing group and the telco work group in particular. And then finally, relative to the first solution around the smart factory, please direct questions there to myself or Yusef Hawar, and we'll get you in touch with the folks at Foxconn and or help you guys directly with anything we can do. With that said, I appreciate your time and the OCP having me here today. And Sumitra, I'm going to turn it back over to you, and so we can finish up.
Thank you, Dirk. I want to, say a big thank you to all of the members, Brian, Dirk, Benjamin, and Yusuf, for your time and presentation. This was a great session. I'm personally excited, to bring in some new work into our group, the Telco and the Open Edge group. And it was great to see Brian's new view, I would say, of bringing in power and energy gap. And I think that's probably a topic that would take more, will pick up in the near future. I know we've been focused on, getting a solution first, but I think power plays a key role in the future, with the energy gap. And so I'm actually very excited, and I would think the community is too, to work on some new proposals, especially with a small cell proposal. And I would like to turn that into actual projects with the OCP community, right? I would encourage all the members to participate and kind of expand on these proposals. Dirk, again, a great presentation, bringing in the Converged Edge platform and tying in the artificial intelligence for your smart factory. And I think there's a lot of work going on with the Open Edge subgroup. You guys have made great progress. So I think we have a lot more use cases and exciting work in the future. Thanks again for a great presentation. And I also got to know about your passion for music. Good luck with that. Again, thanks for the team. And I think we did pretty good on time. And we'll have the next 10 or 15 minutes for a live Q&A. So we'll let the audience ask questions. With that, thanks everyone.
Dirk's on too. We thank you for your participation. Seen the questions have been going in the chat window that we've addressed. I think I don't see any in the Q&A, and I think we've addressed everything in there. Are there any others we're missing at the time? Otherwise, we could maybe reiterate some of the ones that have been in there for everyone's benefit.
I know there has to be a question or two out there from somebody. Come on.
I've been viewing a lot of these things online today, over the past few days and all that too. And yeah, I think it's one of those, you're kind of like listening to stuff, and you're kind of interested, but you're waiting for the right point, and you're not sure when it breaks from recording to reel or something like that. Well, tell you what, while we're waiting, just let's see in the order they came in. We had Andy Billington. He asked if the small cell aligns with any of the work being done under TIP, and I said no. Basically, this is just kind of thinking out loud. When I talked about the OCP 5G small cell, right? That's just my pie in the sky kind of challenge, right? We talk about what's the call to action. So that's kind of just I threw that out there. But it's a total hypothetical thing that doesn't exist, and as far as I know, has not been taken up by anyone officially. But if any of you all listening out there and are think about it or anything else from Bill on down, by all means, let me know.
Brian, I think one came in from Jamal just now, if you see in the chat window. Yeah, can you elaborate on the power demand?
Yeah, Jamal. Okay, well, that's a bit of a broad opening question, so I'm not. If you can type maybe a little more specifically what you're referring to. Are you talking about maybe how I'm saying all the many billions or trillions of tiny devices on the on the load on the edge are going to translate to huge demand on the utility side. Is that what your question's about? We'll have to give them a chance to answer in the chat. And let me pull up the slides, since I think there's something in there that directly.
You got a yes, by the way, back in the chat window.
Okay, good. Yeah. So in terms of that 5G power gap, and if you're looking at the slides, right, then I would direct you to slide number. Sorry, I'm pulling it up in real time myself here, and of course I chose the wrong one. Sorry, I'm trying to figure it out as I talk to you. But anyways, yeah. So what it's saying is that there's all these people say, well, hey, data centers draw way more stuff than this. They're growing. All these micro power devices. Who cares if there's billions of them? That still doesn't add up to much power. You're correct. But if you go, and this is on slide 4 of the presentation, I don't think we have a way to kind of, call it up in real time to share with everyone, but it's in the under the handouts tab there. I summarize this in slide 4, actually, or even there's a graphic on slide 5 that summarizes all this. So what's happening is, because of the inefficiency, mostly in the wireless transmission and the base station itself, that's where almost all of this this energy is lost, and why the parts of the network that have such a high power cost factor multiply. So it's not that it's not the direct power draw of those micro power devices themselves. It's that that just at the edge itself, the wireless transmission, you can lose anywhere from 3 to 6 orders of magnitude in power, which is the power cost factor there. And then there's the base station itself, where you lose another order of magnitude. Well, actually, almost 2. And then there's the rest of the normal utility distribution, which is where that's what puts you on par with the same things like a data center or other networking equipment, where most of their loss are due to this, the utility transmission, and then the just through the power conversion stages losses, which, for instance, for a data center, even including the overhead, the cooling, and all this other stuff, that comes out to a power cost factor of around between 2.5 to 4.5x. But it jumps by several orders of magnitude for those tiny power devices, mostly because of that wireless transmission and then through the base station itself. So when you look at that as a multiplier on that tiny power stuff, then you scale by many billions or trillions of devices, or even tens of thousands on a single served by a single base station or node or something. That's where that highly disproportionate ratio between that tiny load power and the the power plant utility side of things that have to produce it come from. Now, that's a technical power argument. There's also an economic argument, and some of the resources that I put in there in that white paper explains this in more detail, where sometimes it's more, it's not energy limited like you would be from the grid side, but you can be power limited, which means, maybe the base station itself, right, is designed to, for power and thermal, can only deliver so much energy to its loads. So that means that, essentially it doesn't matter if the load side, the little doohickeys, are demanding, 1 million watts. The base station itself can only deliver so much, and that's limited. So that's a power limitation. And that really comes down to more of an economic limitation, because essentially to stay within that envelope, that power and thermal envelope of that base station, even if the load is demanding much more, it means that the load's going to be limited, right? And so you're going to have to sacrifice, either devices or features or how often you transmit or something like that, which becomes an economic limitation, and why it's a power limitation, versus the more utility concern on the 5G energy gap, as opposed to the 5G economic gap, is a concern about grid stability, and a risk to that due to the, kind of the uneven and highly transient load demand. So hopefully we answered. Did that address your question, Jamal? I hope so. Let's see what else we have here. Min says, please keep more deals than we need to go next year. Yeah, you were clarifying there, Doug.
Yeah, I think I answered that question as well in there, but essentially, yes, we were intending to actually bring a demonstration to the OCP conference, but given this moving to a virtual conference, we actually pulled back on that demonstration. But they do have things that's currently staged and ready to go, and the production for this particular solution is scheduled in early 2021. I don't have a specific date. I'd have to talk to Yusef to get that specific date, but we were ready to go. That's kind of the plans.
All right.
Any other questions before we close today?
Let's see, Andy's saying sustainable 5G sounds like an interesting marketing challenge. Well, yeah. Well, see, sustainable is also a relative term, right? Just when we say like greening or something like that, and to me, especially in the power and energy efficiency world, that's been around for some time now, but there's a big difference between a marketing buzzword and, something that is actionable to drive something. So to give you an example, like I come from the data center power world, and, for the last almost 20 years, it's such an emphasis on energy efficiency and the need to reduce, power demand for power costs and whatnot. But in reality, you don't hear much to actually address it, right? How many keynotes do you go to? It doesn't even matter if it's about hardware, software. It could be about anything you want. And somewhere there'll be a mention about the need for energy efficiency, or they'll say our solution's more efficient or better, or it's 27 times better. But you look at data and you ask, well, how are you doing this? Or what do you mean by greening? What actions are you taking, and specifically in the design, the architecture, to kind of, more quantify that? And you don't hear much of that. You hear, no, our stuff is good, it's efficient. Well, that's a relative term unless you quantify it. So in terms of the sustainable thing, there's also just the aspect of, not just being more green or energy efficient in utilization itself, but it depends how end-to-end you're looking at that. More and more these days, we look at the concept of, embodied energy and kind of, what you might call cradle to grave of energy utilization of products. And that's what makes it truly sustainable, which means it's not just the power it consumes when it's being used, but it'll include everything upstream, like the manufacturing, from precious material and raw material processing all the way to, assembly and shipping, and then even post-production in terms of recycling and dealing with hazardous materials and all that. So sustainable is still even a relative term, even in 5G and all that. And, whether it's related to energy or recycling or anything, which also all boils down to energy at the end of the day, is kind of a much bigger topic that should have greater focus. But thank you for bringing that on. And yeah, Andy, you're even saying you work for a railway project. Every conference totally ignores the non-train energy use, right? Good point. And we can talk more about that offline if you want. Still seeing nothing in the Q&A window. And Dirk, I don't know if you have anything to add to any of that other.
Not really. I think it's I appreciate everybody's time and attendance, and I felt like this is a really interesting topic and definitely where the world's going, and I hope everybody enjoyed the topic. Certainly know Brian and I had a big time putting it together, and Sumitra and Yusef and everybody else, so anyhow, let's if there's no other questions, then I suggest we go ahead and close. So.
All right. Sounds like a plan. Well, yeah, I echo Dirk's sentiments. Thank you, and thank you to the OCP community, and also all you guys did for, quite a knee jerk like everything else with the COVID situation, and making this virtual session work. The support has been amazing, and hopefully it shows for the still be useful for the audience and all that. So thank you all very much for the opportunity, and my partners in OCP and everything. And have yourselves a great weekend. Stay safe and healthy out there, folks.